everyone, welcome back. My name is Grace. I'm a newly minted aerospace engineering PhD using her background in physics to analyze gymnastics. Since the semester is over, I no longer have gymnastics gym access, so I've had to improvise and put more of my focus onto the basics and general strength and conditioning. So I've been wondering for a while now if Ithaca has a pull-up bar with a lot of open space around it, and it turns out they do. But the bar is really wobbly. I feel like playgrounds have been getting rid of this type of bar because it's been so hard to find. Probably because of people like me who want to abuse the equipment. Yeah. Luckily, I do have a panel mat, so I can at least do floor basics. So, let's go to practice. All things considered, I think that worked out pretty well for a makeshift gymnastics practice. Only having a panel mat is limiting in what I can do, but it's forcing me to focus on the basics. I'm trying to see this as an opportunity to fix my form. So last week, I introduced the spring and gravitational forces. This week, we'll get into the related quantity of work. Work is a measurement of force acting over a distance. It's measured in joules or BTUs. 1 joule is equal to 1 Newton of force acting over 1 meter of distance, and 1 BTU is equal to 1 pound of force acting over about 778.17 feet. Up to this point, all the quantities we've talked about have been vectors, which have both a magnitude and a direction. Position, velocity, acceleration, and force are all vectors. Work is a scalar quantity. This means it only has a magnitude. The general equation is work is equal to the integral of F dot ds from S1 to S2. On an intuitive level, the dot product is asking how much of the displacement happened in the same direction as the force. Here's a visual. Suppose we have some force vector and some displacement vector. If the two vectors are aligned and pointed in the same direction, then all of the displacement contributes to the work calculation. If the two vectors are not aligned, not all of the displacement contributes to the work calculation. To find out how much does, we project the force vector onto the displacement vector by taking the dot product. We can relate this to the trigonometric identity by examining the projection length. The trig identity we'll rely on relates the angle theta to two of the lengths. The length of the projection of f onto ds is what we want, so we'll rearrange the terms and get the length of the projection of f onto ds is equal to the length of f times the cosine of the angle between f and ds. So we'll use this general form and plug it back in to our general equation. But first, we'll do a little more simplification to the general form. We'll separate the magnitudes from the directions of the vectors with our trigonometric identity expression and the general form of work. Now, the length of the unit vector in the f direction is 1. In the end, we get the integral from s1 to s2 of f times ds times the cosine of the angle between them. The first example we'll go through is work done by gravity. Gravity is nice because it's always pointing towards the Earth's surface. We don't have to worry about springs changing length or forces changing directions. We'll also continue to use simplified rigid body dynamics like we did last week. That means we're ignoring internal forces from muscles, flexibility differences, and technique details. In our simplified rigid body dynamics model, the only force acting on me during my back tuck is the gravitational force. The free body diagram is simply the force of gravity acting in the negative y direction. And the force gravity is equal to Fg is equal to negative mg y hat. Now we can plug this term into the work equation, and that looks like this. Negative mg y hat dotted with ds. In this example, the displacement is how far away from the landing mat I am. Since I'm some height above the mat, we'll replace ds in the work equation with dy. The integrand happens from some initial height y1 to where I land at a height y2. Both of our vectors are in the y direction, so when we simplify this down, we're left with negative mg dy from y2 to y1. There's one more piece of math to discuss before calculating work, and that's the integral. An integral is a way of adding up tiny contributions. It's particularly useful when the quantities that go into the tiny contributions vary. Instead of approximating varying quantities with an average value across our time span or distance span, we calculate the little bit of work done in one instance with a specific value of force and distance and adding it to a running total. Now we can evaluate the integral. M and G are constants, so they do not vary with distance. So we can pull these terms outside of the integral. There's an implicit 1 in the integral right now, and the integral of 1 is s. So when we evaluate the integral, we get negative mg times s evaluated at y2 to y1. When we simplify this out further, we get negative mg times y2 minus y1. And now it's time to pull in numbers from the data. At the peak height of my back tuck, based on my ankles, I'm about 1.928 meters in the air, or about 6.325 feet. Now, we can plug this value back into the formula and calculate the work done by gravity. Using my mass of 47 kilograms, the gravitational constant of 9.81 meters per second squared, and the displacement distance of negative 1.928 meters. Since I'm falling, the sign is negative. We start up high and end low, so that's where the negative comes from. And when we multiply all of this together, we get 888.64 joules. One thing that's important to note is that work only depends on the motion in the direction of the force. Gravity doesn't care if I'm moving left, right, forwards, backwards, or twisting. The only thing that matters is how much I move up or down, because that's the direction gravity is acting. So that's a sense of how work done by gravity occurs. Unlike gravity, the spring force changes as the tumble track compresses and rebounds. The more I compress it, the larger the spring force becomes. That means we can't just simply multiply one force value by the total distance value and call it a day. Instead, we have to account for the fact that the force changes throughout the motion. The tumble track does work as it returns to its neutral state. The distance the spring force acts over are the same spring displacement values we pulled from last week. Once I leave the tumble track, the spring force is no longer acting on me. Even though that force has had an impact on my motion, and I'm still experiencing the downstream effects that relate to my changing position, no work is being done on me by the springs. To calculate the work done by the spring force, we'll start with the general form of the work equation again and plug in the expressions for the spring force. So that's work equals the integral from S2 to S1 of force dotted with the displacement distance. The expression for the spring force is Ks dotted with the displacement. ds and s are pointed in the same direction, so when we simplify this down, we get the integral of s1 to s2 of ks ds. Now we can take the integral and get 1/2 ks squared evaluated at s1 to s2. When we evaluate this expression at the bounds s1 and s2, we get 1/2 k times s2 minus s1 squared. If we recall from last week, the spring displacements were 9.899 centimeters after my round off and 13.883 centimeters after my back handspring. When we plug these values in and solve, we get 40.3 joules and 79.27 joules. So now is the point in the video where I usually try to relate the data or calculation values to something more tangible to non-gymnasts and non-physicists. The 888.64 joules from the work due to gravity calculation is, by definition, the work it takes to lift an object of my weight about 6 feet in the air. For anyone out there watching, I'd say scaling that proportional to yourself, a pet, your kid, or some furniture is going to be the best way to make a connection to that value. The work values from the spring force calculations, though, are a bit less naturally intuitive. The 40 and 80 joule values are more like lifting a gallon jug of water a few feet off the ground. And, to bring this back to my field of research in aerospace engineering, 40 to 80 joules is on the level of work required to deploy a small antenna or release a hatch. They're not huge numbers, but they're large enough that engineers have to account for them when designing space missions. The 890 joule value is closer to what you might expect when deploying a larger spacecraft component, like a solar array or an articulated boom. Anyways, Thanks for clicking and watching. I hope you found this fun, entertaining, and educational. If you like this, please consider liking and subscribing for more post-PhD and physics of gymnastics fun. Until the next one, best regards.